trees. A tree is a collection of nodes in which there is a root node and all other nodes are recursively children of this root node. What does it mean is that root node has some child nodes, those child nodes have their child nodes, and so on. We represent each node of a tree by an object. As with linked lists, we assume that each node contains a key field. The remaining fields of interest are pointers to other nodes, and they vary according to the type of the tree. Binary tree. A tree in which each node can have at max only 2 children is called binary tree. Binary search tree is binary tree. We shall discuss more about binary search tree in the later lectures. We use the fields parent, left C and right C to store pointers to the parent, left child and right child of each node in a binary tree T. If parent of node is equal to nil, then node is the root. If node has no left child, then left C of node is equal to nil, and similarly for the right child. The root of the entire tree is pointed to by the attribute root of t. If root of t is equal to nil, then the tree is empty. Let us look at rooted trees with unbounded branching. The scheme for representing a binary tree can be extended to any class of trees in which the number of children of each node is at most some constant k. We replace the left and right fields by child 1, child 2, so on till child k. This scheme no longer works when the number of children of a node is unbounded, since we do not know how many fields, arrays in the multiple array representation, to allocate in advance. Moreover, even if the number of children k is bounded by a large constant, but most nodes have a small number of children, we may waste a lot of memory. Fortunately, there is a clever scheme for using binary trees to represent trees with arbitrary numbers of children. It has the advantage of using only order of n space for any n node rooted tree. The left child, right sibling representation is shown in this figure. As before, each node contains a parent pointer, parent, and root of t points to the root of tree. Instead of having a pointer to each of its children, however, each node x has only 2 pointers. These are the rooted trees with unbounded branching. The left child, right sibling representation of a tree T. Each node x has fields parent of x, left child of x, and right sibling of x. Left child of x points to the leftmost child of node x, and right sibling of x points to the sibling of x immediately to the right. If node x has no children, then left child of x is equal to nil, and if node x is the rightmost child of its parent, then right sibling of x is equal to nil. Let us look at binary search trees. Search trees are data structures that support many dynamic set operations, including search, minimum, maximum, predecessor, successor, insert, and delete. Thus, a search tree can be used both as a dictionary and as a priority queue. Basic operations on a binary search tree take time proportional to the height of the tree. For a complete binary tree with n nodes, such operations run in theta log n worst case time. If the tree is a linear chain of n nodes, however, the same operations take theta n worst case time. The expected height of a randomly built binary search tree is order of log n, so that the basic dynamic set operations on such a tree take theta log n time on average. In practice, we can't always guarantee that binary search trees are built randomly. But there are variations of binary search trees whose worst case performance on basic operations can be guaranteed to be good. One such variation is red-black trees, which have height order of log n. Another example of variation is B trees, which are particularly good for maintaining databases on random access secondary disk storage. What is a binary search tree? A binary search tree is organized as the name suggests in a binary tree as shown in this figure. Such a tree can be represented by a linked data structure in which each node is an object. In addition to a key field and satellite data, each node contains fields left, right, and P that point to the nodes corresponding to its left child, its right child, and its parent respectively. If a child or the parent is missing, the appropriate field contains the value nil. The root node is the only node in the tree whose parent field is nil. The keys in a binary search tree are always stored in such a way as to satisfy the binary search tree property. Let X be a node in a binary search tree. If Y is a node in the left subtree of X, then key of Y less than or equal to key of X. If Y is a node in the right subtree of X, then key of X less than or equal to key of Y. The binary search tree property allows us to print out all the keys in a binary search tree in sorted order by a simple recursive algorithm, which is called an in-order tree walk. This algorithm is so named because the key of the root of a subtree is printed between the values in its left subtree and those in its right subtree. Similarly, a pre-ordered tree walk prints the root before the values in either subtree, and a post-ordered tree walk prints the root after the values in its subtrees. To use the following procedure, to print all the elements in a binary search tree, we call in-order tree walk of root t. So in this algorithm, as you can see, the in-order tree walk of X is the node. So if the topmost node X is not equal to null, then the in-order tree, then it calls recursively the in-order tree walk using as parameter the left node. So all the left subtree will be considered here, and this whole function will be run on it. And then we are printing key of X. You print that element, that root element of that the topmost element of that subtree, and then again recursively call the in-order tree walk function, giving as parameter the topmost node of the topmost parent node of the right subtree, which is right of X. Querying a binary search tree. A common operation performed on a binary search tree is searching for a key stored in the tree. Besides the search operation, binary search trees can support such queries as minimum, maximum, successor, and predecessor. We shall examine these operations and show that each can be supported in time order of h on a binary search tree of height h. The operations are Search, minimum, maximum, successor, predecessor. Searching. We use this procedure to search for a node with a given key in a binary search tree. Given a pointer to the root of the tree and a key k, tree search returns a pointer to a node with key k if one exists, otherwise it returns nil. This procedure begins its search at the root and it traces a path downward in the tree. For each node x it encounters, it compares the key k with key of x. If the two keys are equal, the search terminates. If k is smaller than key of x, the search continues in the left subtree of x. Since the binary search tree property implies that k could not be stored in the right subtree. Symmetrically, if k is larger than key of x, then search continues in the right subtree. The nodes encountered during the recursion form a path downward from the root of the tree, and thus the running time of tree search is order of h, where h is the height of the tree. The same procedure can be written iteratively by unrolling the recursion into a while loop. Iterative tree search. So this is done iteratively in the same way. On most computers, this version is more efficient. So the key is compared and if k is less than key of x, then x is assigned the value of the topmost node of the left subtree. So the search continues in the left subtree. Or else x is assigned the value of the topmost node of the right subtree and the search continues in the right subtree. And then we return x. And so this is done in a while loop. Successor and predecessor. Given a node in a binary search tree, it is sometimes important to be able to find its successor in the sorted order determined by an in-order tree walk. If all keys are distinct, the successor of a node x is the node with the smallest key greater than key of x. The structure of a binary search tree allows us to determine the successor of a node without ever comparing keys. This procedure returns the successor of a node x in a binary search tree if it exists, and nil if x has the largest key in the tree. The code for tree successor is broken into two cases. If the right subtree of node x is non-empty, then the successor of x is just the leftmost node in the right subtree, which is found in the second line by calling tree minimum right of x. Tree minimum right x. On the other hand, if the right subtree of node x is empty and x has a successor y, then y is the lowest ancestor of x, whose left child is also an ancestor of x. To find y, we simply go up the tree from x until we encounter a node that is the left child of its parent. This is accomplished by 3rd to 7th lines of tree successor. The running time of tree successor on a tree of height h is order of h. Since we either follow a path up the tree or follow a path down the tree, the procedure tree predecessor which is symmetric to tree successor, also runs in time O of h. Insertion. The operations of insertion and deletion cause the dynamic set represented by a binary search tree to change. The data structure must be modified to reflect this change, but in such a way that the binary search tree property continues to hold. As we can see, modifying the tree to insert a new element is relatively straightforward, but handling deletion is somewhat more intricate. Insertion. To insert a new value v into a binary search tree t, we use the procedure tree insert. The procedure is passed a node z for which key of z is equal to v, left of z is equal to nil, and right of z is equal to nil. It modifies t and some of the fields of z in such a way that z is inserted into an appropriate position in the tree. Just like the procedures tree search and iterative tree search, tree insert begins at the root of the tree and traces a path downward. The pointer x traces the path and the pointer y is maintained as the parent of x. After initialization, the while loop in lines 3 to 7 causes these two pointers to move down the tree, going left or right, depending on the comparison of key of z with key of x, until x is set to nil. This nil occupies the position where we wish to place the input item z. Lines 8 to 13 set the pointers that cause z to be inserted. Like the other primitive operations on search trees, the procedure tree insert runs in order of h time on a tree of length h. Deletion. The procedure for deleting a given node z from a binary search tree takes as an argument a pointer to z. The procedure considers the three cases. If z has no children, we modify its parent p of z to replace z with nil as its child. If the node has only one single child, we splice out z by making a new link between its child and its parent. Finally, if the code has two children, we splice out z successor y, which has no left child, and replace z's key and satellite data with y's key and satellite data. In lines 1 to 3, the algorithm determines a node y to splice out. The node y is either the input node z if z has at most one child, or the successor of z if z has two children. Then in lines 4 to 6, x is set to the non-nil child of y, or to nil if y has no children. The node y is spliced out in lines 7 to 13 by modifying pointers in p of y and x. Splicing out y is somewhat complicated by the need for proper handling of the boundary conditions, which occur when x is equal to nil and when y is the root. Finally, in lines 14 to 16, if the successor of z was the node spliced out, y's key and satellite data are moved to z, overwriting the previous key and satellite data. The node y is written in line 17 so that the calling procedure can recycle it via the tree list. The procedure runs in order of h time on a tree of height h.